Let's take a moment to review the results of the previous video. The binomial distribution example we discussed was the tossing of 3 dice. The 2 outcomes for each trial were rolling a 2 for a success and not rolling a 2 for a failure. The probability of rolling a 2 is 1 over 6, and the probability of not rolling a 2 is 5 over 6. We then determined the probability of each permutation. That is, the probability of getting no 2s or exactly 0 successes, exactly 1 success, exactly 2 successes, and exactly 3 successes. To get an equation for a general case, let's look more closely at how we calculated the probabilities. Instead of 2 and not 2 to represent success and failure, let's now use S and F. Next, instead of using the values of P and Q, we will use the letters P and Q to represent any legitimate value of P and Q. To determine the probability of getting 3 successes, we use the multiplication rule and multiply the probability of success 3 times, which is P cubed. For the second case of 2 successes followed by failure, the multiplication rule gets us P times Q, which is P squared times Q. The remaining probabilities are determined the same way, and can be put in this form. Notice that each equation, the exponent for the P term is the same as the number of successes in the permutation. We should also note that the exponent of the Q term is the same as the number of failures in the permutation. Therefore, if X is the number of successes in a permutation, then P, the probability of success, taken to the X power, is one factor of our general equation. If there are X successes in N trials, then N minus X is the number of failures in N trials, and is the power to which we raise Q. Now we need to notice that each term is multiplied by the number of times the relevant permutation occurs. For example, the permutations of SSF, SFS, and FSS are the same combination. In a previous video, we developed an equation for the number of combinations of n objects selected X at a time, which we will use as a coefficient to determine the number of permutations with the same combination. This will equal the probability of X successes in n trials. This portion of the expression determines the probability of a combination having exactly X successes and n minus X failures. This portion of the expression determines how many times the combination with X successes out of n trials occurs. Let's use the parameters of the last example to verify this equation. Remember, the probability of success equals 1/6, and Q equals 1 minus P, or 5/6. The number of trials in this example is 3 and is the value of n. To find the probability of 0 successes in 3 trials, we substitute these values into the equation with X equals 0. First, we substitute 0 for the variable X in the equation. Next, we substitute 3 for the variable n. Then, substituting 1/6 for the variable P, and finally substituting 5/6 for the variable Q, resulting in the expression that we now need to evaluate. Remember that 0 factorial equals 1. The factorial terms become 3 factorial over 3 factorial. 1/6 to the 0 power equals 1, and 5/6 taken to the 3rd power is 25 over 2/16, which results in 125 over 2/16. To find the probability of getting 1 success out of 3 trials, we let X equal 1 and substitute the other parameters as before. The factorials expand to this. 1/6 to the 1st power is 1/6, and 5/6 squared is 25 over 36. The factorial term reduces to 3. 1/6 to the 1st power times 5/6 to the 2nd power is 25 over 2/16, resulting in 75 over 2/16. Next, we let X equal 2 and perform the same calculation, and get a result of 15 over 2/16 for the probability of 2 successes in 3 trials. Finally, for X equal 3, and substituting the parameters of this example into the equation as before, we get a result of 1 over 2/16. These are the same values we calculated earlier in the previous video. Now that we have an equation, we can consider any value of n, any value of p from 0 to 1, and any value of x from 0 to n. Let's now graph the distribution. We'll start with the example of 3 dice where n, the number of trials, equals 3, and the probability of success equals 1/6, approximated here to 4 decimal places. Earlier, this equation was used to calculate the probabilities of x equals 0 through x equals 3. They are repeated here. The expected value of a distribution is the value of x that is most likely to occur. The expected value is calculated by taking the sum of the products of each x value and its probability. For the case of x equals 0, that would be 0 times 125 over 216, which is 0. For the case of 1 success, we multiply 1 by 75 over 216 to get 75 over 216. Making the same calculation for x equal 2 and x equal 3, we get the results of 30 over 216 and 3 over 216. When we take the sum of these numbers, we get a value of 1/2 or 0.5. This means that if we were to toss 3 dice a very large number of times, the number of successes per toss of 3 dice would average 0.5. There is of course no way a single toss of 3 dice could result in 1/2 of a success. The expected value is the average or mean number of successes after tossing 3 dice many times. For a binomial distribution, the expected value or mean can be calculated by multiplying n times p. The Greek letter mu will be used to represent the mean. The standard deviation of a binomial distribution can be found by using this equation. The Greek letter sigma will be used to represent the standard deviation. These 3 equations pertaining to binomial distributions will be used again in later videos. Let's go back to the example of 3 dice. Previously, we calculated these probabilities. We'll now convert them to their decimal equivalents for the sake of the next illustration. Let's note the probability of getting 0 successes is the most likely outcome, and getting 3 successes is the least likely outcome. The likelihood of getting 3 failures is much greater than the likelihood of 3 successes because the probability of success in one trial is rather small. Let's increase the value of p, the probability of success, and watch what happens. As the probability of success for one trial increases, the probability of 0 successes decreases, while the probability of 3 successes increases. The probability of success for one trial is now 1/2. Clearly, we are not talking about the tossing of 3 dice any longer. This could be the tossing of 3 coins where we define landing heads up as a success and tails as a failure. The probability of getting 3 heads in 3 trials is the same as getting 3 tails. As the probability of success for one trial increases further, the probability of 0 successes continues to decrease, and the probability of 3 successes continues to increase. These 3 equations tell us the probability of getting exactly x successes in n trials, the mean of the binomial distribution, and the standard deviation will be used again in later videos.